Hello.
Hello.
I think it works.
I can't see you, but I can definitely hear you. Oh, there you are.
It works now.
There we got you. I don't know if we've got you plugged in. It's in my computer.
All right.
It's not very loud, is it? Well, thank you very much for joining us, David.
No problem.
Yeah.
Hopefully I'll pass on something useful.
Yeah. Just give me 1 sec here. My audio is a little off. I just want to make sure we can all hear you okay. Apologies. Okay. Who's my tech department?
Caleb.
There we go. Who's tech?
Okay,
You guys. Is audio in? Max.
Is the audio output of the call not going through?
It's just, yeah, it's not going through.
Oh, it's through Zoom, isn't it?
Yes, through Zoom.
The Zoom settings anywhere?
No.
It should be, maybe it's under secure, because I know, just through the thing, click the up arrow there.
Let me just check to see, as I think it's the wrong
Settings.
it's not using my headphones. Let me microphone is that.
Yeah, I think we're hearing you better now, David.
I hear you well.
Okay.
I think the problem is that Zoom didn't pick up the fact that I was using earbuds, and it was working off the speaker and the microphone on the computer instead.
Okay, no, we got you loud and clear here. Before we get started, are you okay to just tell us a little bit about yourself and how you got into this?
Sure, I can do that. There's a little bit of background.
Yeah.
I started working in artificial intelligence back in about 1982 in one of the first wave of artificial intelligence. I ran an AI lab and a software development organization. I was the head of engineering for that. So we spent about 10 years doing principally research and development projects for the Canadian government and other organizations into what was at that time leading edge software for artificial intelligence. So we did expert systems, we did neural networks, we did fuzzy logic, we did genetic algorithms, which I'll talk about. Did things like trying to automate the air traffic management, things like trying to figure out how much money to put in ATM machines based around holidays and usage and geography, air quality in buildings, detecting types of bugs that were being found on ships to identify whether there was ecological problems going to come forward based on shipments that were coming into port. Primarily advisors type systems from a knowledge-based system. Did some work on the space station, looking at planning algorithms for how you move the equipment to the ends of the arm and move the arm around to execute tasks.
The Canadian arm.
Yes.
Oh, cool.
Yeah. I also helped design the operating system for the Canadian arm.
Oh, we were learning about the Canadian Arm 3 just a little bit ago that that's going to be orbiting the moon.
Right.
Right. Oh, cool.
This was the very first one.
What's your connection? I mentioned that I was having speakers in, and I was talking to my brother, and he said, "Oh, I know this guy," and he mentioned you. What's your connection to Todd?
So I work for I'm a contractor into the same organization Todd is stationed in, which is the Chief Force of Development for the Canadian Forces. And so my role is trying to determine what the military information technology, computers, sensors, all that sort of stuff will look like in 30 years. and how advanced technology from quantum computing to artificial intelligence, machine learning, all of that sort of thing will have to be used, or will impact how the Canadian Forces work moves forward, and what sort of systems or what sort of programs they need to put in place in order to be ready to use that technology.
So projecting into the future, what in probably a bunch of different possibilities of what might happen. Is that the idea?
Well, yeah, looking at emerging technology and saying this is where it may have an effect. This is the type of effect it might have. So when you start to look at things like quantum computing, and you start to look at being able to send the quantum state through free air, and create that same state on another machine, what can you do with that? How can you use that, for example, as a one-time key for cryptography? If you've got a n-dimensional parallel computing machine based on quantum computing, how would you use, what sort of problem space would you use that to, as compared to a Van Neumann, the standard computer you're used to using, or a massively parallel computing system? So, it has its advantage in different areas. Where would that be? How would that then fit into the military concept? And then what do they need to do to go from today to that point?
Okay. Well, I've shared my screen, so anytime that you're ready, David.
Okay, so you've got my slide deck up?
No.
Oh no, I don't.
You need. Okay, no, that's fine. I can share. I'll share. I wasn't sure how you were running this.
Yeah, sorry about that.
Okay, there we go. We'll go into project mode, hopefully. There we go. So what I was going to do today is walk through the following agenda. A little bit to talk about what is AI, to situate this. And then what do we mean by an algorithm? What is an algorithm? Everybody's got their sort of vision of that, but it's important to understand that an algorithm is more than just bytes and bits that are put together. And then how do you build AI systems? So, a quick look at expert systems, machine learning, neural networks, fuzzy logic, and genetic algorithms, and other approaches that are used out there to make AI systems. And then look at a short history of AI and computing, where the current focuses are for AI today, and some of the issues and challenges people don't think about when we talk about using AI to run, automated cars and that sort of thing. And then open up for questions. So what is AI? The shaded box is, the definition that you'd see all over the place. It's the theory and development of computer systems, and it's important that it's computer systems able to perform tasks that normally require human intelligence, such as visual perception, speech recognition, decision-making, translation between languages, logical reasoning, problem solving, learning. Those types of things are where you would apply what we consider AI. And so, it's a logic-based learning from experience is a really good area. Building something based on an expert's capability that you can then give to a technician or a junior person who can then rely on that expertise to get better as they're doing on the job. To abstract knowledge from information or from data, to take that, mind, the stuff that is not, it's doesn't require a lot of thought, but it takes a lot of time, and to take that and bring it up into something that an expert can work with, to do analysis and provide conclusions based on a set of information. Those are the types of things that we use AI, and that's when we talk about AI, that's the problem set that we are thinking about. It isn't usable for everything. There's lots of applications that you're going to use classical software, lots of applications where there are other approaches object-oriented programming, other things that are far better. So it's a small set of problem spaces that we actually apply this to. Next thing is, what is an algorithm? And it's the description of how you do a change or how you walk through a problem. And so there's a couple of definitions up there, but the key thing that you should take away is an algorithm doesn't have to be running on a computer. When I was going through, there was a stream of courses where we had to build an algorithm, and not just the computer system, but we had to build the same algorithm using RC circuits and regular electronics. We had to build it using hydraulics. We had to build the same system using mechanical gears and levers and switches. And they all ended up doing the same thing. And so the key point is, when somebody talks about an algorithm and programming something, it doesn't necessarily mean you're programming on what we call the Van Neumann computer, which is what you have on your desktop. There are other ways to do it, other ways to think about that problem space to allocate it out and allow it to execute and come to an answer. So what is AI? AI has potential. Oh, sorry. How's come this is going backwards? Excuse me. So how do we? So there are a number of ways that we build expert systems or build AI systems. And typically we think about expert systems, which are the way that a lot of the AI was done in the 80s. There's not much of this going on these days because object-oriented design tended to overtake the space of those problems we're solving. Fuzzy logic, I have a slide on each one of these, is another mathematical approach to understanding the probability of different outcomes and allocating that out into your algorithm. Genetic algorithms is a way of training based around the set of possible inputs with possible outcomes that leverages how genes split and recombine in order to find the best solution. Neural networks is another approach of taking training sets assigned to an answer where there's all different algorithms for putting the training set against the answer and changing all of the configuration of all of the what they call nodes in between in order for them to always come up with the right answer no matter what training set you put in. And then there's a number of other approaches to how you do this.
Dave, those genetic algorithms now, they use those, is that like, do they actually use those to look at genes, or is it just the name of it? I didn't catch that part of it.
No, so it's a name because it leverages the way genes split in terms of how the training goes on. So if you've got a case where you've got 30 variables that define the problem area, and you have an output or a result, and you find that it doesn't quite work, you've got 10 different training sets. You take maybe half of this one and half of that one, and you try them together. And then, if it gets better, you continue down that path. If it gets worse, then you use some of the other ones. So it's more the splitting idea of how genes are split to make, when the two, in conception, when the two male and female come together and they fertilize, the DNA splits and recombines. It's that same idea of the DNA is the problem set, and you recombine the problem set to get the answer.
Okay.
So it's just a mathematical approach on how you train to come up with a set of inputs that always creates the right output. So again, the expert system was one of the earlier approaches And as we'll see later on, it's one that's starting to reappear. It's one that I did a lot of work in, where you take your if then else construct and you're essentially trying to separate the control of that, of the steps you go through, away from the data that allows you to make the decisions. And you separate them out and you have a algorithm that recombines them to make the process steps depending upon what data set you put in. So you essentially take this if, and there's an antecedent that comes out of your data set, then some consequence that comes out of your data set, you put those data set pairs together, and you then add intermediate steps that something has been proven. And as you get data, it will slowly build the walk to a conclusion based around what data and when the data is presented, which is a very different approach than an algorithm that you typically program in C or in any other computer language, where the data has to be valid at the time the if statement gets there, or you go a different route. This will allow you to slowly add data in and eventually come to a conclusion. This is the sort of things that we were using to do planning systems. So the Mars rover, which a friend of mine was responsible for the program management of, that we all see still running around Mars, was the algorithms for how it functions were all built with this type of logic. And one of the problems with dealing with a robot that's, you know, that far away is the radio frequency, the waves that we're sending up with commands and the information coming back can take 10 minutes. So when we send it a command, it doesn't get it for 10 minutes, and then it sends us the response back and we get that 10 minutes later. So it's a 20-minute round trip to command and tell the rover to do things. All the data we're seeing is 10 minutes old. And if you think of playing on a computer game, if your avatar is actually 10 minutes ahead of where you think it is, and you're telling it, giving it commands to do something 20 minutes ahead of that, or 10 minutes ahead of that, so 20 minutes from now, that's a very difficult problem when you're doing something that's moving constantly. And so in order to manage that time difference and what goes on between commands, they've got built rule-based systems up there to tell it how to interpret what it should be doing and make best decisions in between. The other problem is you only get to talk to it for about an hour a day because of the rotation of the two planets. You only have line of sight between the Mars rover and Earth for that very short period. So in order to get it to go for that 23 hours and 10 minutes or whatever it happens to be, you have to have it understand what you really want and be able to make decisions and how to deal with running into a rock and other things you haven't anticipated. So this is the type of technology that was available at the time the Mars rover was being designed. It's the type of technology that's being used to actually make it run. Everybody talks about machine learning, and the fuzzy logic, the neural networks and genetic algorithms are sort of loosely coupled as what we mean by machine learning. And the intent or what this is we've developed mathematics that allows us to take a input vector and an output vector, take hundreds of them, where each one represents a different conclusion you want it to draw based on a different input set, and train different types of systems to reconfigure themselves so that for those input vectors, you get the output vector. The neat thing about it is once you've trained it, things that are close to the input vector will also map closely to the output vector. So it's just not a one-for-one, it's a many-to-one learning around that, that training vector. And the three approaches of fuzzy logic, genetic algorithms, and neural networks are three approaches for how you train the inside mechanisms of the program to adapt from that training vector to the output vector. So, and yeah, once you're done with that, we call what you've got an inductive algorithm. And what we can then do is to reduce down the input, the representation inside into a very fast executing algorithm. We call an inductive algorithm that we can then put on what you've probably heard of as edge computing. So on your Google device or your phone or your Siri, your Alexa or what have you, we can then take that problem, speech recognition or other things that we've trained it on, and we can put that into those devices in the small chips, so that we can do that processing at the device. So neural networks. Yeah.
That machine learning, and is that all the same type of stuff that's used to make like climate predictions, and like you have an input that's in, then you would have then being able to run some data to look at multiple outcomes depending on what the initial input is? Would that be the same?
So if you know what your output would be for a set of inputs. So for example, we did some work with the Environment Canada years ago, where we took satellite pictures of the North Atlantic, and they would go and say, this picture has a hurricane in it. This picture has another type of weather pattern. This picture is forming a hurricane. So we'd take 500 pictures where the MetTech had said, this is what I see. And we put that through a neural network and trained it so that it would come up with the same answer. And then you could take other weather satellite pictures and put it in there, and that would say, this is a hurricane forming. Okay, so it is good for some of those sorts of things, but if you don't have the knowledge a priori to train it on, then this is not a relevant technology. So as I was saying, this diagram here, you have a number of boxes on the left-hand side, the input layer. And if you think of that as a vector, it's a set of values. It can be 1, 0, or it could be a real number for each one of them, but they have a meaning. It could be a pixel position, or it could be a value to a sensor that you have around your house for predicting, or for your windows and doors, or it could be hard, things like the stock as this, here's the value of these stocks that represent a cross of how the world is performing. Whatever you choose, but as this is a very difficult part of the analysis or the design of your neural network, but you have these inputs, and for each one of them, you go and say, this is the result. This is so for the example with the satellite pictures, that would be, each one of those would represent a pixel on the satellite image, and the output would be, this is a hurricane, this is not this is just a developing hurricane, or this is clear weather, or whatever it happens to be. And you have the different layers, which are the circles, where you are essentially doing what they call a cross product between the input and a weighting value that's inside. And that gives you a result that is then fed into the second layer, where you then do another cross product on that result, and out of that comes your answer. Obviously, when you start, and that's just random numbers in there, it's nowhere close. You now take the result of that and you work backwards, adjusting the weights in each of these nodes, and feed in the next vector, training vector, and you continue this and loop and loop and loop until eventually you get all the right answers for all the training sets. And that's essentially how a neural network is trained and works. And then the next time you put a new vector in that you've never used before, it goes through those nodes and will come out with one of those answers where it's closest to. So it may be a whole new one, but it will come out as the closest one. So if you're looking for a wire and a bomb in the suitcase, and you get part of the wire, but you don't get the whole picture, it would show up and say there's a potential bomb, even though it only sees part of what you're looking for. So it's, it's very good for that interpretation of it and extending out to include additional information that gives it a closeness to an answer. Fuzzy logic, you take those input vectors and you ascribe them to a membership, and you then use a Boolean logic on that to come up with that output, and based upon their assignment into the fuzziness of how close they are to being right, you can change that fuzziness or that closeness vector, and again you can train so that input vector comes out with the right answer. Just another mathematical model. Genetic algorithms, as I said earlier, it's based around the idea that we can treat that vector as a DNA strand and that input vector, and we can train based upon our original set. If that doesn't come down close enough, instead of changing all the weights, we can recombine and move around the input vectors until we eventually get a really good result. And so there's work going on using that type of technology for planning. If I have, different plans, and some of them come out with a good result and some come out with a bad result, and I bring the best of the best and the worst, the best from the best and best from the worst, and add them together, maybe I have a better solution in terms of a plan. So this type of an approach is being used a lot in planning algorithms. How do you move, solve the Tower of Babel and these sorts of things is the type of use for this type of a mathematical approach to learning. There are other things you've heard of, maybe natural language processing, the whole approach to how do you take the digitalization of speech to create words, and then from words integrate them together into an understanding of a sentence and an intent from that sentence in order to improve the performance of things like your search engines. Or how do you use that to go into databases? Semantic networks is a way of structuring relationships between entities and reasoning based around the entity, that relationship, to draw conclusions. So these are all different approaches used today in artificial intelligence. There are others always being developed, and as pointed out, these are mathematical approaches to problem solving. There's no magic to it. It's just we've developed some very complex mathematics that allows us to look at problems and look at algorithms in new ways that aren't just covered by the standard language that we use in C and other computer languages. So short history. The whole idea of developing calculating machines and other things started a long time ago, and there have been quite a number of people that have developed mathematical models to try and represent information and knowledge, and leading to a very famous person, Charles Babbage, an Englishman, and in many ways considered the father of programming or father of computers. He and Ada, his girlfriend and assistant in the lab, who the computer language Ada is named after, built the first machine to do arithmetic, and she programmed it to do all sorts of solve all sorts of astrological problems for the Royal Navy. It's really the first computer ever built, and it's all mechanical, as I said earlier. That when you think about computers, don't always just think about the digital thing in front of you. Leonardo da Vinci, was extremely interested, and a lot of his designs are based around mechanical computers. And then in 1768, we start to see around that time mechanical computing devices becoming a form of entertainment, and the little dolls down there were all designed with mechanical computers inside to do things. So the little fellow with the feather in his hand could write 40 characters out on the sheet, and they would bring these guys out onto the stage, and people would sit in the stage and pay money to watch these machines do things, play the piano and write and do that sort of thing. And the most famous one, of course, is this one here, which was a little duck that you would put food in, and it would walk across the stage and drop, it would excrete things on the stage as it went across. And this was a very, a very famous and a very sought after thing to watch. So that's the early stages of where this whole thing of computers and AI and everything else comes from. In the 1950s, we didn't have the computing infrastructure, but we were starting to see it, and there was a lot of people starting to postulate about what we would be able to do with the Van Neumann machine. And I keep reusing that term, but the Van Neumann machine is the computer you have in front of you. It refers to an architecture that a man by the name of Van Neumann designed about this time for moving data from memory into an arithmetic logic unit, executing code based on, or executing things on using a clock and pushing that data back out into memory. So the whole basic process of doing any program step all runs through this ALU and is all based around his architecture for how you do it. It's a very specific architecture for computers. There are others that are out there we don't see much in the commercial world, but are used for very specialized things like parallel processing, image processing, and things. They tend to be on satellites and on military systems and what have you. In the 70s and 80s towards the end of the 80s is really when the AI winter happened. But that, as I said earlier, that's when I was involved heavily in this field. There was, at the very beginning, there was a lot of optimism that the computers had got to the point that they could actually support this sort of processing. And so there was a lot of R&D, a lot of effort to build expert systems, to build neural networks and genetic algorithms. What we found is we could do small expert systems quite successfully. As I said, the Mars rover is using that technology. But when we started to do big neural nets, that neural net we talked about for the satellite imaging, we would set that up and start it processing, and it had maybe 500 training vectors in the input that we were training on. And we would come back once a day and check on how it was going. The training algorithm, the was going. It was all automated. And after a week or so, we'd find it had settled down in what would end up being a false minimum. What I mean by that is it was close enough to the right answer, that it got stuck, but not close enough to be right. And so we'd have to go in and change some of the weights and get it restarted. And, after a month, we would have it trained on the training set we had, and then we'd take it to the client, who would go, yeah, that's not quite right. We really should have come to this conclusion here. I know I told you that, but I was wrong. And we'd retwink everything, and we'd do it. Obviously way too slow to be viable for anything but a research project. So they just found that the computing processing, the infrastructure to support this technology just wasn't there. And as I said earlier, the object-oriented programming was taking off as a very good way to go beyond the logical capability of the standard programming language. And so all the effort ended up going into that. And a lot of the stuff we could do with expert systems, you could also do with object-oriented programming. So the whole world started off in that direction. In the 90s, the games took off and language interpretation took off. And that's really where AI started to focus, was on supporting games and supporting language, search engines and that sort of thing. And into the 2000s, we start to see more of the robotics. The neural networks were getting to the point where they could support a lot more of the robotic work that was underway. And so you see Romba came out of MIT about that time. Rod Brooks, who was the head of the lab at MIT, he had developed a concept around using insect intelligence to drive robotics. And then by insect intelligence, what he meant was very small algorithms to deal with each part of the device. Rather than build one big program that dealt with the whole robot, he would build an algorithm that dealt with the foot movement, and one with the knee movement, and one with the hip movement, and etc. And they would be independent, and there would be a very small feedback from each of those to the others, so that they could self-correct. And he built a whole bunch of robots for searching down through the pyramids, for looking for lost people in collapsed rubble after buildings fell. And his most successful, or his most relevant from a commercial perspective, is Romba, the little vacuum cleaner. And that originally it was not neural nets. Today, a lot of it is more pushed by neural nets, and a lot of the the mules and the walking robotics all came out of the work that was going on at this point in time. And then we get today, where we've got those robots have evolved so that they can dance and jump and recover from being pushed around, and they're now becoming useful for protection details, for carrying things. We've got Waymo here just down the street from where I live, that's out with autonomous vehicles that drive around without passengers in it, or drivers in it. And everybody's familiar with the home devices that are out there. All of those have significant amount of AI built into them to support the speech recognition, to support the searching, that sort of thing. The next wave being neuromorphic computing, which is where we've hit the point where, once again, the Van Neumann architecture is not sufficient to satisfy the needs of the neural networks. And so we're now talking about going to a new form of computing infrastructure, or hardware, based around more analog than digital, so more of an analog computing capability. more of a feedback and in order to support the the nodes that we talked about in the neural nets. So we're now looking at moving away from the hardware that we've been using for the last 40 years into a whole new form of computing infrastructure to support the robotic or the autonomous capability that we're now on the verge of seeing commercially available. So issues with all of this, mapping the physical problem characteristics into that vector is very difficult. In some cases, it makes sense, but if you think about a car and you want to put a neural net for should it turn right at an intersection, what are the input vectors you need on that? What are the sensor data that you need? You need to know where everything is around you. You need to know the state of the road, the weather, all sorts of things. So what's the full input vector that you need in order to make the decision that it's safe to turn right? It's a big problem. And training sets and their completeness. How do you know that for that decision to turn right, you have sufficient training sets to actually train the neural net on? So when we talk about that Waymo computer, the training set for that car is somewhere in the order of 1 million training sets. And each of those cars, they drive around my neighborhood and they all have enough computing power to run a server room in the back of them as they collect the data and they process it and they try and learn from driving around. It's a huge, complex problem. How do you maintain them? How do you do configuration management? How do you decide you need to change? Which one do you change? There's some really big problems to trying to make this technology work. To do that neural training session with the training set for the Waymo car, you're talking about billions of teraflops. That's a lot of processing, even when you do have fast computers. It's hours and hours and hours of computers churning away in order to take that training set and come up with the next version that you're then going to drive around and test and collect data as to why it did or didn't do it right, recompute your training sets and do this over again. And then once you've done that, in order to make it useful, you have to go through that algorithm it's produced and identify where unused nodes are. There will be, when it's collapsed down, if you had 3 layers of nodes and you had 500 nodes in each layer, maybe 10 of them aren't being used, or maybe 100 of them aren't being used. Well, how do you identify those and remove them? How do you realize that out of the 3 layers, 2 nodes in layer 1 and 2 nodes in layer 3 are doing the same thing? Can you identify that and collapse them and remove them so they don't have to be computed every time a decision is made? And how do you test and verify, especially when you're putting a robot in a room with people, or you're putting a robot on a road to drive with other people? How do you test and verify that you've actually got something that is sufficiently safe? And then how do you certify this? These are all things that we grapple with every day, trying to figure out how we're going to integrate this technology that's coming at us into the real world and enable it to actually function beside us. So other issues, causality. When a machine learned or a system that's been trained comes to a conclusion, it has no idea of what it's actually doing. We don't understand how it got there, why it made the decision. So there's a whole bunch of ethical and other issues, safety issues around that. How do we ensure that the system it builds is itself protected from hacking and spoofing and other things when we don't really understand what it's doing. How do we understand the limits of the algorithm? You know, when you have trained it on a data set, as I said, you put a new one in, it comes out with an answer that's as close. But what if it's outside of its knowledge bound? What if you put something totally out from left field in? It'll still give you an answer and it'll still move forward because it has no ability to know it did not understand the problem. And so there's a whole bunch of issues around there of that type of a problem that we have to deal with in order to include this technology. All right, questions?
All right, I'll just get the lights here, Dave. See if we can view. There we are. Get the lights, guy.
Yeah, just click it. It'll adjust.
All right. Well, thank you very much.
Just let it. There we go.
Let our eyes adjust.
You're welcome.
Yeah. Any questions? We got. They're looking. They're thinking. I guess the question I would have for you, like, you know, having all of this knowledge on artificial intelligence and understanding computers, does it ruin science fiction movies for you, or there's some?
All the time. My wife hates it because we'll get partway through a movie and I go, I can't watch this anymore. This is just dumb.
Yeah. So, like,
yeah.
what would be a popular one that you're like, ah, oh, man, that's not even remotely close?
Well, I know the one that sort of stands out is Sutherland in 24. I couldn't deal with that one. You know, a lot of these ones where they, you know, have the computer team in the background doing their cyber stuff, and you go, I'm sorry, you know, it doesn't work that fast, and you know, you can't get across air gap computers and a whole bunch of these sort of things. It's not so bad if it's sort of like, you know, a real science fiction that, you know, there's no tie to the real world. But if they're trying to do the real world and they're bringing in technology, it's hard to watch.
Yeah. Oh, yeah, nice and loud, Lucy.
Because one of the things that actually got me a bit more interested in the idea of machine learning and stuff, don't kill me for this because I don't know what it's going to be like. But I do remember specifically watching iRobot and wondering what that was like, because I know that one at least does its best to try and work off of a somewhat feasible vision of how they would work. And it does bring in things that I know are real, but I don't know to what extent it is, and it just, or if it's just completely bull.
I'm afraid I haven't seen it, so I can't really say much about that.
Oh yeah, that.
It had the three laws of robotics thing, and the whole like, it had the whole like trolley problem thing throughout it.
Yeah.
Yeah. Well, the big problem is, of course, that we're not at the point where the type of intelligence exists in a computer to think about its actions. So when you start talking about a machine that is actually making decisions about the ethicalness or the correctness of its actions, that's way beyond our ability to program in. Just even defining it in order to develop an approach to how you would deal with it is difficult, because the whole it's a concept that we've embedded into society that itself is changing. You know, what is socially correct today was not, or 10 years ago is not today. What is considered an appropriate interface is no longer correct from what was. So trying to develop an algorithm that says this is the way, this is what is acceptable. This is a an ethical behavior or whatever. When we have, we're not consistent on it, it's very difficult.
Any other questions, gang?
Jacob.
Jacob.
What was your favorite project that you worked on? Or one
So
that-
the one that was, so we built did a research and development project for the Department of Transport in Canada years ago to look at essentially removing air traffic controllers, so the technical issues and technical feasibility of using AI to do that. And it was just a lot of fun. Very challenging mathematically, very challenging at that time from a computational perspective, because it was one of the larger expert systems that were built in the 80s. And very, very good to see our ability to actually, not in real time, but to essentially do all of the work that an air traffic controller could do with an algorithm.
And did it work? Is it something that's implemented?
It worked, but not in real time. And that was the crutch, right? As it actually eventually had to be executable in real time. And as I said, that's what we found in the 80s, is that we could solve a lot of things with the technology, but we didn't have the infrastructure to make it available or usable in reality. So we could take the Canadian airspace, and both where the radar systems are and where there's no radar, which have different rule sets, put all of the traffic that was up at that time and predict all of the potential conflicts, come up with solutions for how you would deal with it. But we couldn't do it in a timely fashion to enable it to replace an operator. But then we were running R&D, so we were, that wasn't our goal at the time. When Hughes Aircraft were hired by Transport Canada to try and take that technology and actually make it something that would be usable in reality, they couldn't do it because the processing, the computing capability wasn't there.
So question I would, so you mentioned you worked on, you were part of the Canadian arm when it would first happen. If you were to just kind of, just go through some of the projects that people might know of, or different designs that you have been a part of, just a little name drop, I guess, session.
So we built for Public Works a software system to help their inspectors going into buildings to look for and identify air quality issues. So, there's people are getting sick. What's the symptoms? What do you see as you physically walk through, looking at the infrastructure, water stains, mold, this and that, what have you. What's the likely reason why the people are getting sick? What sort of sick building syndrome are they having? Which is quite useful. We built a system for the Argentinian immigration or customs folks to look at incoming container ships. And when the container ship comes in, the inspectors go in looking for bugs. They do samples throughout the container ship, trying to identify the potential for invasive species to come in. And so, they find a dead bug. What is it? Is it a problem? Is it likely that there's going to be eggs on board? Do they need to fumigate? Do they have to turn it around, send the ship back? These sorts of things. And so we built an expert system to help inspectors understand, identify the bugs and understand what sort of reaction they needed to take.
And so that would be a combination, like with biologists as well. Like I guess you would need to know the life cycle.
Right. Yeah. So, the experts were biologists who worked for immigration. So our job was to sit with the immigration officers and say, okay, what sort of bugs do you see? Where do they come from? You know, so this is a ship that's come from China. These are the 10 bugs you might see. What do they, you know, what do they look like? Where would you most likely find them? Those sorts of things they would put in, and then that would lead to, as an inspector goes around putting in data, things saying, oh, you should go look over here. You should look at this, and oh, you found something great. You know, is it this or is it this? And lead them down through identifying what the bug was and what the remedial action was.
So there's so many different applications of AI, you know, no matter what the discipline is, I guess there could be some use for using it. Just we had a math class join us for this talk as well. And I just wanted to touch a little bit on that. Like, was math always something that you were you really interested in? And kind of what type of math would be something that people would want to focus on if they were interested in this type of work?
So yeah, I always found math interesting. But I'm an engineer, not a mathematician. And when I went through, we had a choice. You could become, if you wanted to work in computers, you either became a mathematician or electrical engineer. I made the choice electrical engineering. That said, from a calculus perspective, I actually have more calculus than most mathematicians do. Just because they tend to spend more time in algebra and algorithm development and theorem proving and things, whereas an engineer you tend to spend more time using the calculus to understand the physical world. So, you know, a lot of math, absolutely. If you're going to go, you know, as a pure you know, learning algorithm person and, you know, neural nets, you know, understanding how they work and what the algorithms are and creating new algorithms for learning, probably definitely mathematician's degree is far better than an engineering degree. But you also need the computer science. You know, computer science is split out of those two professions, taking parts of both worlds into it. And so, you know, a lot of the other parts you need come from the computer science side.
So you have like with your company, like you would have different people contact you, like, so you have a contract with the military that you do some things with, and all kinds of other different people as well. Like, how do they just contact you and say, hey, I got this problem?
So right now I'm semi-retired, so I only do this stuff with your brother because it's fun. When I was doing the AI work, you know, we had 50 people. It was a fairly, you know, it was a large small business in this, and we were the largest company in Canada doing AI at the time. And so yes, people came to us because we were known.
Any other questions at all, gang? Do you want to think?
Oh, sure.
Yeah.
On behalf of the Academy of Inquiry and Adventure Okanagan, I just want to thank you so much for coming out here and teaching us about AI. It was so interesting. So thanks so much.
Yeah, definitely lots of things for us to think about. I'm still a few slides behind, I think. So that's good. Yeah.
It's a very big topic to try and squeeze into a short time. And I didn't want to delve into too blistering detail. I wanted to give that sort of broad brush of where the world is and why it's got there and where it's going. Hopefully that you'll find that useful as you progress your studies.
Mm-hmm. What would you say would be like, you know, like, I guess the holy grail of AI? Would it be a sentient machine? Would that be like, where do you think it's going?
Well, it won't get there in my lifetime.
Yeah.
At this point, you know, it really is about the trying to think of the right biological term here. The brainstem level functioning of things. You know, we're not into you know, complex extraction of knowledge and reasoning at a really high level. It's coming, and you know, but we've got to build the computing infrastructure because we're starting to hit the ends of what the current technology at the hardware level will support. The next big wave is going to be moving it out to edge computing. So building these things and then transitioning them out into the appliances and out to the edge. And another big thing is, as I said earlier, the expert systems disappeared. But one of the things that we knew back then, and that were starting to come out as a new discovery, is you eventually need to have something that pulls it together for goal-driven behavior. And so the next wave is going to be to start to use neural networks and genetic algorithms to do the very quick processing, reaction, balance, these sorts of things. But then we need to start that goal-driven planning, thinking type, expert system type thing. So I think you'll start to see that type of an approach of on top of the neural networks as a new wave in the next 5 to 10 years.
All right. Well, thank you very much for your time, David. Much.
You're welcome. Have a good one.
Bye-bye. Take care.
Thank you.
I have recorded this. Are you okay if we put this on our Facebook?
He left.
He left.
He's gone.
I think that's a yes.
He never said no. So that's fine.